that's out there. And of course, recovering geometry is a fundamentally difficult problem in computer vision. Here's a picture. You look at this monocularly and you see a surface with some geometry on there. There's a certain ambiguity perhaps as to what's in front and what's behind. But there's a question of, well, how do you get a single image to understand this kind of stuff? You, of course, have all these problems that image intensity changes as a function of the illumination. But here's an image of same scene lit from different colored light. And, of course, it provides a different image to be processed, and yet the geometry is identical. We've talked about this before, challenges of scale. Here's an interesting picture. When you look at this table, you see a bunch of white bowls, cups, etc., whatever. But if we actually were to sort of take a look at just in this patch right there, clearly there's not a whole lot of interesting variation going on there for image processing to handle. And somehow it basically has to be able to somehow figure out from the basic extraction of this shape that there's this cylinder on the table. And that's generally a hard thing to do. We also have trouble that color is not all that discriminative sometimes of what's there. So there's sort of a similarity between the foreground and the background. What we'd really like is we'd like some representation, something that gave us the shape directly. And so that we would see something that looks like this, and it won't surprise you that this is where we're headed. So here is a bunch of objects on a table. And, it'd be nice if the system could just know that this was one surface and that this was another surface, and these were the objects. And what we're going to do is we're going to talk about 3D sensing. There are a couple of ways of doing 3D sensing, some of which we've already seen. So passive 3D sensing, what do we mean by that? That means you don't use any active illumination. That is, you take the world as it's given to you and you somehow sense that. And maybe you exploit some known geometry of the properties or something about the scene. So have we actually done something that recovers geometry of the scene? Well, of course we have, right? We've done stereo. In fact, those of you who are participating in the class for credit have actually matched stereo images. So here's an example of some stereo rigs. These are sort of amateur ones. I love this one, right? Build the wooden blocks, screw two cameras on, capture a picture. Here's something a little more sophisticated where you've got some high-end video cameras mounted on a rigid bar that you can control the divergence angle. But of course, if any of you have gone to the movies lately, you've probably paid a lot of extra money in order to be able to entertain your two eyes separately, or more precisely, to see movies in 3D, stereo. And here's the types of rigs that they use. Some of you notice that's Spielberg on the right. In the middle, I think that's James Cameron. He was behind the making of Avatar. Avatar was one of the first movies where 3D was fundamental to sort of the experience of the movie. And there had been a lot of 3D movies before, and it's obviously one sense, but in this non-film critic's view of the universe, it was a seamless blending of sort of what you would think of as normal imagery, but done in 3D along with computer graphics. And so the 3D experience wasn't just sort of the experience of 3D, it was actually crafted as part of the movie. At least this is my view of the universe. And it's when it really made it, and the technology had come around quite a bit with polarized light to really be able to give you a compelling 3D experience. There are other ways also of getting depth from a natural image. One cool one, and we actually talked a little bit about this when we were talking about focus pull, right, is that the way a lens works, focal plane is actually in focus, and then when things that are further away or in front are not in focus. So you can go from focus to depth. All right. In fact, here's this cute little animation of this scene, right, where you can see that they're varying the focal plane, and by varying the focal plane, you can figure out the depth of different parts of the scene. All right. So that's all passive. But the other way of doing 3D sensing is what we refer to as active 3D sensing, where somehow you're projecting something out into the environment or sending some energy into the environment and reading that energy back in order to recover depth. So we actually talked just a little bit about photometric stereo when we talked about photometry and the idea that you could recover shape if you had known light sources. So even though these are thought of as regular images, it's actually an active sensing technique because you're lighting the system in a controlled way that you know about. But when most people talk about active sensing, they talk about something that creates sort of special signals or pictures. So an obvious one is just bounce something off a surface and wait to see how long it takes to get back. All right? So there are different methods of doing that. This is a little guy. He has these little ultrasonic sensors, okay? If you go way back in time, back in the Wayback Machine, I don't know if it was the 70s or 80s, the Polaroid cameras started doing active sensing. They actually had a little acoustic sonar chip on them that would send out what's called a chirp, and then based upon how long the response took, it knew, based upon the speed of sound, how far away the thing was, and it would focus the camera. One of the interesting effects of that is because they made so many of those cameras, it made those sonar things very cheap. So people started putting them all over robots and things like that and using sonar to detect depth. Much more sophisticated is what's called LiDAR, or a laser rangefinder. There's two of them here. One is on the side over here. One is stuck in here. These are on a PR2 robot. These actually generate a slice, and they send a little beam out, and they wait to see how long it comes back. Now, of course, that's a lot faster than with sound, okay, but it's measurable. But you only get a slice of depth. So then what you actually do is you put it on a little device that goes up and down like that, and so this little front area actually sweeps that plane, and it produces a 3D depth image that way. So that's these are referred to as time-of-flight sensors. A more sort of traditional, or I'd say fundamental computer vision method of doing active sensing is what's referred to as structured light. So here's the stereo figure that you might remember that we used before. The idea was we had two cameras, right, and there was some point out here, and that point would project, whoops, missed the line there. Okay, that's better. It would project to this point here, it would project to that point there, and because I knew which 2 points they were, I could figure out the triangulation, all right? Well, structured light says, instead of having a camera over here, I'm going to put a projector. And what this projector is going to do is, instead of having a sensor here that notices where a point is, and remember we had to go look for the point, what we're going to do is we're going to send things out this way, right? So we're going to send some particular, think of just one point for a minute, right? And then in this camera over here, we're going to see where does that point show up on the image plane, and then we can do the triangulation. But instead of doing points, what we actually do is we project stripes of some sort. In fact, sometimes this is called light striping, right? And here it's shown with colors that makes it real easy. And the system, of course, knows where each of the colors lies on its plane. So then in the right image, in the right camera, the only camera, we see a picture that looks like this. So what you can see here is like when these things are bent like this, okay, as it comes closer to you, right, so it comes over here, it moves to the left, and so the line moves to the left there. In fact, you can see that a little more clearly in this image here. All right, so we have a set of hands, and these are the light stripes that are projected on them. And actually, this is observed in just the right-hand camera. And here what you're seeing is a 3D reconstruction of this surface based upon that light stripe. So basically, by doing this light striping, by projecting these stripes out and then seeing them over here, I can recover a full 3D model. All right, so that's one form of projecting something out. Lately, there's been a huge growth in using infrared structured light. All right, in infrared structured light, one of the nice things about it is you and I can't see it. So it's doing all this stuff out there, but it's not sort of interfering with our vision. And the main reason that IR structured light has become so big is because of this puppy right here, the Microsoft Kinect. All right. Kudos to my friends and colleagues in England and Cambridge who helped take the technology, and it was the 3D technology that I'll tell you about was actually developed by PrimeSense, which was an Israeli company, and then Microsoft leveraged it in a way to go from the depth to recovering skeleton, which is a whole other interesting piece of work that we won't talk about here, but if we did it in machine learning, since they use machine learning methods for doing it, we could talk more about doing that. But the Kinect is really, I mean, it was $150, so all of a sudden you could put depth sensors on little experimental robots for very little money. So how does the Kinect work? Well, it's not public, all right? So there are people who know exactly how Kinect works, people from PrimeSense, et cetera, but it's not public. Lots and lots of this stuff is known, but the exact implementations are not known. The PrimeSense patents describe at least two ways, and I will tell you about both of those ways. Kinect Conventional wisdom is that one of the ways is actually used in the Kinect and one is not. I don't really care. They're both kind of interesting. So the two methods that they use, one is a very, very clever optics trick. In fact, it's so clever I don't totally understand exactly how it works because I have to get more into detail. But essentially it projects a pattern with two different kinds of lenses, and we'll talk more about it in a minute, that allows you to go directly from the image to the depth. We'll explain that. And then the much more standard way, which is just like light striping, is that you're essentially using something about the projected image from the projection of a particular pattern in what it's observed like in the other camera. So you're about to see some drawings that look kind of funky. They don't look like, you know, the high-quality drawings that Megan always insists that I use. But that's because these are actually taken directly from the patent and the patent applications. I think it's cool to just see those. So the key to the Kinect, the key to the prime sense focus method are these cylindrical lenses. So cylindrical lenses, if you take two of them, and you have one that goes one way, and I think on the next thing you have one goes the other way, you end up with this funny situation where you have different focal lengths depending upon which way you move. So you have one focal length horizontally and a different focal length vertically, and of course slightly different focal lengths as you were to sort of rotate around. What this allows them to do is to project out speckles, and now what happens when a dot is out of focus? Well, in a normal lens, right, it becomes a blurry circle. When you have one of these, what are called astigmatic or asymmetric lenses, it becomes an ellipse because the lenses are different in one direction than they are in another direction. And what's cool about the way they did this geometry, and this is the part that I'd have to work through the math more to understand, is that depending upon the depth, so here the hand is at one Z and here's at another Z, again, these are from the patent, these ellipses, well, they have different thickness, but more importantly, they have different orientations. So you can just take a look at the orientation in a little local area of these little dots that have been smeared, and the orientation tells you the depth. This is really, really cool. But I think it's so cool that they probably don't use it, because I think it requires some pretty precise lensing and some other things. I'm not really sure. But this is the one method of how the Kinect works. And if you go in their patent, you'll see figures that talk about like this, that you capture this test image, and then you find the range based upon the pattern orientation. And then you build this 3D map. Although you notice this says based on offsets between test and reference pattern, so that's the method I'm about to tell you. Here's the one that just talks about the orientation. So what about the more standard method? The more standard method is actually just like light striping. So you recognize this figure. This was the light stripes where we project out the stripes, look at them from a camera, and then we see that the stripes bend depending upon the depth of the object. So as we said before, you're still just doing stereo, okay? Except instead of two cameras, you're actually doing projection of one and coming at the other. But the thing that I want to remind you about stereo is if you know the relative geometry of the cameras, you know how they're aligned and their offsets, etc., right? Their extrinsics and their intrinsics, right? Then, for any given location in one image, there is an epipolar line, remember, in the other image along which to look. Now, this is also true for the projection method, right? So if I project a point out, right, at some location in one image, then depending upon the depth of the scene in my other image, yes, I'm over here, Meg, in the other image, where that point will be along an epipolar line. And how far along the line it is a function of the depth. So I only have to search along a line if I know the calibration. Well, in my Kinect system, of course, I know the calibration between the projector and the camera. But instead of projecting lines, what we're going to do is we're going to project out a speckle pattern. So instead of a regular projector, we're using a Kinect. Instead of line stripes, we're spraying out a pattern of, they call them pseudo-random speckles, because it's important that the pattern be a little different everywhere so that I can do a, ready, normalized correlation. All right? So instead of using a camera, I use my Kinect, because the Kinect actually, if you take a look at it, has a little projector in it and a camera. And the relationship between those are known. And then what the camera sees is a speckle pattern, but where the dots are offset as a function of the depth. So that's shown here. So here's a picture. So it's looking flat. This is from one perspective. It's actually sort of faked in how it's doing it, but don't worry about it. If it was just a flat wall, but if I change the depth, so I put a little book on this stand, right? You see that's the difference between